Now, I'm going to discuss about gradient projection method. And this method is used to solve unconstrained problem. Suppose we are given a function and we seek to find the maximum or minimum value of f of x with an initial point xj. This method is useful to obtain the maximum or minimum value. Assume that we are finding the maximum value of f of x and suppose it occurs at some point A. Using only the current point xj, we move to a new point xj plus 1 in such a way that we approach the optimum at the fastest possible rate. Now, our desire is to move a distance s from a point xj to the point xj plus 1. Then the component form for an I-dimensional space of the point xj plus 1 is given by xj plus 1 I equal to xji plus smi. Here s is given as the distance moved and mi is the direction of move for the ith component. Suppose our function is f of x in an n-dimensional space. We take a small step ds in such a way that y increases or decreases as much as possible. This distance of move is given as ds equal to root of dx1 square plus dx2 square plus etc plus dxn square. That is equal to root of sigma I equal to 1 to n dxi square. We assume that our function y is differentiable. Then the change in y associated with the set of displacements dxi is given as dy equal to dou y by dou x1 dx1 plus dou y by dou x2 dx2 plus etc plus dou y by dou xn dxn. That is equal to sigma I equal to 1 to n dou y by dou xi dxi. Then dy by ds equal to sigma I equal to 1 to n dou y by dou xi dxi by ds. Here, a particular set of displacements will make dy by ds large or small, and that gives the direction of steepest ascent or descent. Then our problem has reduced to a form maximize or minimize dy by ds equal to sigma I equal to 1 to n dou y by dou xi dxi by ds subject to ds equal to root of sigma I equal to 1 to n dxi square. Now we solve the problem using Lagrangian function using a Lagrangian multiplier lambda, and we write it as f of x minus lambda g of x. Our f of x is sigma I equal to 1 to n dou y by dou xi dxi by ds, and g of x is 1 minus sigma 1 to n dxi by ds whole square. This is obtained from ds equal to root of sigma I equal to 1 to n dxi square. Squaring ds equal to root of sigma I equal to 1 to n dxi square, we get ds square equal to sigma I equal to 1 to n dxi square. And dividing this ds square term in both sides of the equation, then we get 1 equal to sigma I equal to 1 to n dxi by ds whole square. And we get the equation sigma I equal to 1 to n dxi by ds whole square minus 1 equal to 0. And this equation is taken as g of x. This is the function g of x. So we get sigma 1 to n dou y by dou xi dxi by ds minus lambda into sigma dxi by ds whole square minus 1, and put it as equation 1. Differentiate this equation with respect to dxi by ds and equating to 0, we get dou y by dou xi minus 2 lambda dxi by ds equal to 0, and put it as equation 2. Now again differentiate the first equation with respect to lambda and equating to 0 we get sigma I equal to 1 to n dxi by ds whole square minus 1 equal to 0 and put that as equation 3. From 2 we get dxi by ds equal to 1 by 2 lambda dou y by dou xi and put this as equation 4. From 3 we can write sigma I equal to 1 to n dxi by ds whole square equal to 1. And by squaring and summing up the equation 4, we get sigma I equal to 1 to n dxi by ds whole square equal to sigma I equal to 1 to n 1 by 4 lambda square dou y by dou xi whole square. From above, we know sigma I equal to 1 to n dxi by ds whole square equal to 1. So we can equate 1 and 1 by 4 lambda square sigma 1 to n dou y by dou xi whole square. From this we get 2 lambda equal to plus or minus root of sigma equal to 1 to n dou y by dou xi whole square. Our mi is dxi by ds and from equation 4 we know that 1 by 2 lambda dou y by dou xi equal to dxi by ds. Substituting 2 lambda that we obtained above, we get mi equal to plus or minus dou y by dou xi by root of sigma equal to 1 to n dou y by dou xi whole square. This positive sign of mi gives the move in which y increases and negative sign of mi gives the move in which y decreases. Consider the problem of steepest descent. Let function be y of x equal to x1 minus 4 whole square plus x2 square and find the minimum point given an initial solution 0, 0. So our function is y of x equal to x1 minus 4 whole square plus x2 square. Our initial solution is given as 0, 0. So we can write the xj plus 1 component as x2 equal to x1 plus smi. Mi is given as plus or minus dou y by dou xi by root of sigma equal to 1 to n dou y by dou xi whole square. Here our problem is to find the minimum point. So we take mi as minus dou y by dou xi by root of sigma equal to 1 to n dou y by dou xi whole square. We find dou y by dou x1 and we get 2 into x1 minus 4. Dou y by dou x2 is obtained as 2x2. Dou square y by dou x1 square is obtained as 2. Dou square y by dou x2 square is obtained as 2. Dou square y by dou x1 dou x2 equal to dou square y by dou x2 dou x1 equal to 0. Then we find m1 and m2 at the initial solution 0, 0. Firstly, m1 at 0, 0 is given as minus dou y by dou x1 by root of dou y by dou x1 whole square plus dou y by dou x2 whole square, that is given as 8 by 8 equal to 1. Then m2 at 0, 0 is obtained as 0. Then we substitute these values in h2. h2 is given as x1 plus smi and x1 is 0, 0 and mi is given as the first term m1 is 1 and then m2 is 0. So mi is 1, 0. And h2 equal to 0, 0 plus s into 1, 0. Then we get h2 as s comma 0. Now substitute this h2 in y, we get y equal to s minus 4 whole square plus 0. And differentiating this y with respect to s and equating to 0, we get dy by ds equal to 0 implies s equal to 4. And we substitute this s value in h2, we get h2 as 4 comma 0. At h2, we find y of x and we get y of x equal to 0. Now we consider the Hessian matrix. H of x equal to dou square y by dou x1 square, dou square y by dou x1 dou x2, dou square y by dou x2 dou x1, dou square y by dou x2 square. Substituting the values we got already in h of x, we get h of x equal to matrix 2, 0, 0, 2. We know that here h of x is positive definite, and that's why the stationary point we obtained, that is 4, 0, is minimum.